So can you be able to see my screen?
I can see.
Okay. So in our last class, we have learned how to draw the molecule first and how to do the adjustments and the labeling and get the suitable positions, appropriate position to label. Then that's all. So now here we are going to draw the pi interactions and any other CH pi interactions or hydrogen bonding interactions, everything. So in today's class, before we draw this one, so I have already got this molecule. We must know how to get the other molecules. So only when you open the zip file, only one asymmetric part will come here. So the only one molecule with this solvent we had, but additionally I got two other molecules. So I deleted. And I will show you how to get this. First, I delete those things. If you want to delete anything, then you can select like this using this arrow key, arrow tool, and drag and leave it wherever you want. Then within the square, whatever the atoms covered within the square or the rectangle will be deleted if you press the delete button after that. Then we can enlarge and see whether any other atoms are left without deleting, then you can delete. So still we have two atoms here, two molecules. So we can delete one of that because I have already obtained those things. So I want to show it again how to get it. That's why I'm deleting. Okay, now we have only one. So we have only one molecule. So with this, now we can go to the list file. Now it is here. The list file is here. So I won't just open it and open and see. Can you see this list file now?
Yes.
Okay.
Yes, we can see.
Okay. So then you can go down and in the middle, we can see the pi-pi interaction table. So if you're familiar with this file, then we can easily find out. Otherwise, first time it will be difficult to search and find the exact place where the pi-pi interaction table is there. And later it will be easy. So these are the ring interaction. After seeing this, then you can slow down scrolling. These are 5-membered rings. So how many rings are there? All rings will come one by one. So this is the first ring, CG1, and this is CG2. This one is CG2, the 6-membered ring. First one is 5-membered ring, including the metal part, molybdenum, and the other coordinating atoms. And the one ring that also will be taken as one ring. The first ring, CG1, and the CG2 is also that is also 6-membered ring, but that is a 6-membered ring, but it is also the coordinating ring, that is including molybdenum, the central metal atom. Here, these are the things, atoms included in the ring. Molybdenum 1, O1, C15, C10, and C9, N1. This, and after that, this is CG2, CG3. This one is 3. See, this says this is CG3. So we have atoms, these atoms. So this is a 6-membered ring. This is a normal our benzene ring. CG3 and CG4 here. There are 4 rings, and that is also another benzene ring. That's all. Only there are 4 rings. So we need this ring. That's why I'm telling you the information how to find out that ring. Which ring is CG1, CG2, CG3, CG4. Only 4 rings are available here because we are going to find out the CG-CG interaction. That is the centroid ring pi interaction between 2 rings. This is the table. Okay. And now what we can do is we can just this is CG1 and CG1. Now we can first check the CG distances, because from the distances only we will select whether these are significant interactions. So if it is above 4 angstrom, then we usually neglect, unless we have no other interactions except these things. Then in that case we will consider those things, because without having any interactions, it will not assemble together to give crystal. So in that cases, then we will consider it as a significant case. In the other cases, if we have more stronger forces like hydrogen bonding and other CH pi and the metal or any other strong interactions, then we will not consider above 4 angstrom. So in that cases, then we don't need to consider these very weak pipe interactions. Anyhow, we can see there is a interaction with this 3.6925. So we can analyze this interaction. And again, the similar thing is here. That is CG3, CG4, and CG4, CG3. Those are same interactions. I mean, in distance also same. So this can be considered as 1. And again, we can see another interaction with a distance 3.97, almost 4. But you can see whether it is significant or not. Still, we cannot say whether it is because it's around 4. So sometimes we can neglect those things if it is not relevant. And we can see the slippage also in the same case. The slippage is listed here. So if you look at the slippage means that if a pi interaction is just direct, parallel to each other, then it will be slippage will be 0. Then if it is slipped somewhere here, then the CG, if you connect the CG and the normal to the ring J, then it will give some angle. So the distance will be high. So if it is, if the slippage is higher, then the interaction will be weak. So in those cases, then we will not consider those as a significant interaction. That we have to analyze some of. Then first we can eliminate those things all above 4, and then we can come to this CG3, CG4 that must be analyzed. That may be significant, and there's only one. And CG4 also we can see, because with the CG4 ring, there are two interactions. If CG3 and CG4 is true, and again we need to neglect the CG4 interaction, because CG4 one ring, it cannot interact with the one side with the CG3 and other side with the CG4. Therefore, in that cases, we can neglect the CG4 interactions if the CG4 and CG3 is significant. If you look at the CG3 and CG4, the slippage is 0 point. Here the slippage is around 2. So the slippage is higher for the CG4. So in that case, we can conclude that CG4 interaction is not significant, and also the CG distance is also almost 4 angstrom. But here it is somewhat considerable. So we can conclude that only CG4 interaction is only available. So this is how we can decide how many pi interactions are available, and that depends on the case. Each.
So what is the relation between slippage and CG?
Yeah, slippage is that if it is just directly parallel, then the slippage will be 0. So if it is slipping like this, so the interaction will not be that much significant between the two rings. So it will be reducing. If it is exactly parallel to each other, then the interaction will be higher. So that's why we are just checking the slippage also, and it is found that it is 2 here and higher slippage, but for this it is less. So in the case that will be almost parallel. So it will be very much close. The distance also will be less in this case. The CG distance also will become less than this. Here we can obviously see that the distance CG interaction is higher for this, but in this case is small, 3.6925. But in this case, they are 3.97, almost 4 angstrom. This is how we can decide, even though that this is not exactly the way to neglect it. But if it is, if there are no other significant interactions, then we can consider these as well. That depends. So we should, and in some cases, even the editors or the reviewers will ask you to include in some cases if they find that is significant when we neglect. So that happened in our case also. In one case, our Dr. Zeller, he had asked us to include one pi interaction that was between the alkene, like a C double bond C, and the metal. So in that case, we neglected those things, but he asked us to include those pi interactions. So in one paper, we have included that also. He showed that there are some other interactions, and request us to include. So in those cases we include, otherwise we usually neglect those things. But here in the table, it will show if it is less than 6 angstrom, it will list all the weak interactions. But we need to find out more significant interactions. Otherwise, we can simply say that there are several pi-pi interactions which is above the CG distances are above 4 angstrom. Very less significant interactions or very weak pi-pi interactions. So we can state like that also in addition to that. After mentioning these strong significant interactions, we can write a sentence saying that there are some more additional weak pi-pi interactions which is having the CG distances of more than 4 angstrom. So that statement can be written because we have the evidence. So now we can see how we can draw this. So after finding this, now we can see how to draw these interactions. CG3, CG4. So we must know what are these CG3 ring and CG4 ring and the symmetry. This says the asymmetric residual unit, ARU. This gives us the symmetry. This is 1 and this is that is a I ring and J. This one is J. Second one, this is I. So there are 2 rings involved. If we consider this as I, and this will be J. So I and J ring. So if this is CG3, this one is CG3, and this will be CG4. So likewise, if it is the original molecule, that the asymmetric molecule, then we have to find out the symmetric code of this. Then that symmetric code is given here. So if it is CG3, CG4, then the symmetric code is 3666, 666. So that is given here. So 3666, the symmetric code is this: 1 minus x, comma 1 minus y, comma 1 minus z. So this is the symmetric code of that we can take that one also. So how to draw molecule with this CG3? Already we have in the IE, we have CG3, but CG4 is also in the same molecule. But we need another molecule to have interaction with the CG4 of the neighboring molecule. So the neighboring molecule with this symmetry, 3666, different symmetry with a different symmetric code. So that we have to draw it here in the. So now can you see this diamond software, sir? Now.
Yes, sir.
Okay. So now we can get the molecule. Try to get the molecule. Other molecule. So we know the CG3. Before that, we have to get what is CG3. So I already told you that that CG rings, that all rings are here. This is CG4. This is CG3. This is CG3. So we have to consider this C2, C3, C4, C5, C6, C7. This is the C3 ring. And CG4 is from C10 to C15. Okay. So now we can go back here and find which ring is this. There are 1, 2, 3, 4. There are 4 rings. So we can check. This one is this is C14. This is C10. This is C11. So this ring is CG4. So this ring must be CG3. So you can check again. Yeah, C4, C3, C2, C1. So this ring is CG3. So we can start with this CG, with this molecule CG3, and find out the CG4 of other neighboring molecule somewhere here or here. So that we have to obtain. For that, how to obtain the other one? That is to obtain that one, what we have to do is we can click one of the any atoms that is in the CG3 ring, and before that we have to set here, go to build and connectivity. And in connectivity, what we are going to do is we are going to find out that other molecule which is very much closer to this ring. Then only we can find out the other ring. It will be very close to that. That is around 3.6, 3 point something. No, we have seen around less than 4. So we can set the distance between this carbon atom and the carbon atom of this CG4 ring. So we can set the distance of this carbon atom and this carbon atom is the maximum of 4 angstrom. So then what will happen is when we refresh it or obtain the nearest polyhedron, then it will search and find out within the distance and bring all the other atoms which is within the range. So from that we can find out the residue of that one. Then we can get the whole molecule from there. So this is the technique that we are using here. So for that, what we have to do is we have to increase the distance. Usually we will not get this carbon-carbon distance will not be much higher distance, means not about around 4 or 3 angstrom. So it will be 1 point. It will be 1 point. We can see the carbon-carbon distance here. Carbon here. This one is carbon-carbon. The minimum distance is 0.828 and the maximum is 1.656. So this is the maximum distance that is the default distance. Usually it will be within that. Then only it will automatically draw the carbon-carbon. It will automatically connect the carbon-carbon. This software will connect the carbon-carbon bond, carbon atoms together, and it will consider it as a bond within this distance. So now what we are going to do is we are going to increase this to 4. Then it will search and connect all the atoms within that limit. So it will find out all the atoms within the range, so in the radius. So and just give OK, and then select one of these atom, select these and right click and find the fill coordination sphere around the atom. Then it will bring something, but the thing is it will connect all other atoms as well. So we have to extract from that. So we can see it will connect everything, whatever within that sphere. So we know what are the other usual atoms. So accordingly we can select those atoms and even delete those things, because this is connecting all other atoms here. So we can select and delete those. And here also we have many other atoms that we can delete. After deleting, again this is unwanted. So whatever we know that molecules, therefore we can easily handle those things and drag it down, and see, rotate and see whether which it is connecting here and there. So we don't know which one is that. So we can just check all these atoms whether they are CG4, belongs to CG4 atoms, CG4 ring. So look at this. This is C12. C12 belongs. This belongs to CG4. C11 and C10 belongs to CG4. So therefore we can delete the others. These are not needed at all. And what about this? This also we can check again. C14, that is in the CG4 ring. So we can leave it. So now we can rotate and see the here, other side also one atom is left without deleting. So we can delete because we have found the atoms within the sphere. Then again, now what we have to do is we can now delete these atoms, the bonds here between them, because we don't want that bonds between them. But we need to find out that whole molecule. Now the residue is found. So now we have to find out the whole molecule of that residue. So we should not forget to bring that distance that we have increased back to the normal, because this was in 1. So for easy remembrance, I usually increase this number, not this number. If you increase this number again, memorizing all these, the default number is maybe difficult. Therefore, I only increase this and delete unwanted things, whatever comes within that range. And later, I will change to the default value. So again, okay. Otherwise, when you select this and bring create molecule, it will connect with another molecule also within that range. Therefore, it is very dangerous. Then you will get more molecules there. Therefore, don't forget to again bring that into normal. So now we can click any of these atoms or all atoms and right click and select this complete fragment. So this is a fragment. The complete fragment means the whole molecule will come. So now it will come. Okay, now it came. So now you can see the other molecule next to this. Now we can, now we can easily see that atoms, sorry, the rings CG3 and CG4 here. This is CG3. This is our original one, CG3, and we found the nearest molecule now with this CG4 ring, which is almost parallel to that. So this has the pi-pi interactions between this ring and the CG4 of the other symmetry. This is the other symmetry. This molecule in another symmetry. So now we our duty is to draw the solid, the graphical representation to show pi-pi interactions between them. So there is any other ways also that we can simply connect these atoms like this, connecting this and this, and now we can go to picture and bond design, atom design, make insert bond. So go to build and insert bond. When you go to build and insert bond, then we can click two atoms like this, then it will make bond here. Then click this and this, it will make bond. This and this, it will make bond. And this, select this and this, automatically it will, when you select two atoms, it will make bond between them. And this and this, it will make bond. This and this, they are here, so it will make bond. So you can just have a representation to show that we have some interaction between this ring and this ring. This is also, we can draw like this also. And at the same time, if you want to draw and show it by dotted lines, not like the solid line here, then you can select those lines by pressing the Control key and select all the lines and click on the selected rectangle. No, it is. So I will show only for one, and edit. Go to edit and bond design. If you go to bond design, and here you can select, even if you want to change the color of the bond, then you can change the color of the bond. And then thickness also you can change if you want here. And the radius, that's fragments. Here we can bring it to broken lines, like dotted lines. So if we give just 5 fragments in the lines, and it will be broken. So those lines will be broken like this. Or if you want to even go to edit and again bond design and change even the colors, so blue color. So it will become blue. So we can select like this, select all the, and go to edit and bond, and we can select blue, then broken lines 5. That's all, and all will become like this. So in this way also we can show that there is a significant pi interaction between this string and this string. If you look at this, this is also the same. You don't need to draw again, or even with the same color you can represent it, because this is also the same interaction. This is CG4, this is CG3 at the same interaction. So we can show it in ones, or even we can with the same color. If you use different color, then it means that you are having two different pi interactions. But if you use the same color and same, you can put it as a CG4 and CG3 underneath, then it will be considered as the same interaction you are showing twice. Or no need to show it. This is one way, and another way is for this string. Shall I show it for this string, the same interaction but for this string? So that we can do it again by using solid cylinder. So we can put it like this, so that I can clearly select all the atoms here, and one select. By selecting this, by clicking the control key, we can just click on the atoms, whatever we want to connect, or we want to have a draw the interaction also as cylinder. So here also, so we are going to connect these atoms and these atoms and these atoms together by using a solid cylinder. Okay, so I have selected all the 12 atoms here and here. Then after selecting, then you can go to build and polyhedra. Here construct polyhedra, and then you can go to design, and in the design here you can select a blue color or whatever it is, whatever the color you want. And the transparency also we can select usually, but if it is a very solid color which doesn't have any transparency, or you want some kind of transparency also, usually I like half transparency, so I just give half, means 0.5. Somewhat you can see the other atoms behind. At the same time, this cylinder also will be visible. If you give 1 transparency, then the solid cylinder will not be visible. So it should be within 1 and 0. So you can give accordingly whatever you want, then it will be okay. Then select OK, and the cylinder will be formed between the selected atoms. So now, now here there will be a dummy atom to draw this polyhedron. Therefore, we don't need this dummy atom. So we can select this dummy atom and right click on that and go to edit and atom design, then make it we can bring the transparency, or we can make the transparency or invisible. We can make it invisible, so it will not be visible at all. So now you cannot see that atom. So now just you can consider it as a Here you can see that transparency is there, so that you can see the atoms behind this cylinder. So it will be somewhat very nice. So this way or that way you can represent these pi-pi interactions, which whatever the pi-pi interactions you have found is significant in this crystal structure. Okay, then now one interaction is over. Now we can move on to the CH pi interaction, which is also there in the zip file. So we can move on to the zip file. Yeah. Now these pi-pi interactions are over. These are the pi-pi interaction table. And then next to that, it will be at the CH pi interactions will be there. So you can easily find next to the pi-pi interaction, and that table will be there. So easily you can find that also. The X means XHCG. X can be other atoms, and the hydrogen is important from that donor atom, hydrogen, and the ring. So the ring is here. This hydrogen will be here, and this is the donor atom. Then this interaction will be the hydrogen between the hydrogen and the ring pi electrons, between this hydrogen and pi electrons. So now we can analyze this also here. O5H5CG1, one interaction. And other interaction is C4S H4SB, between C4S and H4SB, one interaction with this symmetric chord. You can observe the symmetric chord here.
Sir?
Yes, yeah.
Sir, is there any other types we can represent that pi-pi interactions? Because I saw in some other papers, pi-pi interactions is represented in other types also. Is there any other, only two types we can?
A pi-pi interaction. Can you just explain it, what you have asked?
Sir, actually, we just now we discussed about two types. It means one is that line and another is polyhedra. Two types we interact.
Or drawing way of
yeah.
representing. Yeah.
Drawing. Yeah.
Yes. Yes. You are asking any other type of ways, any other different ways to show?
Yeah. Yes, sir.
Maybe, but I don't know. Only we use only this polyhedron type, that one. So in some cases we have used that dotted lines also, because some people say, some reviewers they don't want to make the picture clumsy. They in that cases they will say remove that polyhedron or something like that. In that cases we will put dotted lines. Mostly they all like this kind of, because it is very significant to show it by drawing cylinder. So it seems that some kind of interaction is there. So it gives a strong clear picture that it has some interaction. So mostly they in most cases they accepted, everyone. Only few cases we met in that cases. In those cases we have handled and used that one, dotted lines. Then they accepted.
Okay.
Otherwise, we need to draw using not even this diamond. With the help of other softwares also, even Photoshop or other things also, we can draw some other graphical things, whatever we want. But whether they will accept or not, that we don't know. But this one they accept mostly. Mostly means more than 95% all papers they accept with this polyhedron type. So you can use polyhedron, no problem. All will accept. Okay, then this CH pi interaction, and we have to check this also. But this HCG distance, we can see this distance, whether it is very high or very short distance, and also the angle. Here is XHCG angle. This is very low, and these are somewhat okay. Angle means that X means the donor, H is the hydrogen and the ring. So if it is broken like this, if it is less than 90 degree, then it will not have much overlapping. Then if it is like this perpendicular, it will be very high overlapping with this p orbitals of the ring. Therefore, the angle, when the angle is increased, then it will be more, it will have more interaction. So we can see those things as well. And the gamma also can be considered. Gamma means that angle between the CG, actually the CGH. CG is a ring, and CG and the hydrogen here, that will come like this, now in angle, and the normal from the J, the ring. So the angle between this and the CGH vector. So this is the gamma. So that gamma is, if the gamma is less and almost zero, then it will have more perfect interactions. So very extent of interaction will be higher. Therefore, in these cases, if you analyze this, this has less interaction, and these two cases can be considered. And let us see, but we cannot decide, but we can just we have to, anyhow we have to go there and see whether which type of interactions are there before we conclude. And here C4S O5HS CG1 O5HS H5, sorry, H5 O5H5 CG1. Let us see that whether it is feasible or not, whether it is possible. But we cannot believe on this completely, because this is a calculation only. So based on the distances between those atoms and the CG centroid of the ring, then it will list all the distances and show us these are the distances and all the angles. So our duty is to find out whether it is really an interaction or just merely a distance because of something else. So sometimes what happens is the distance will be short, but that may be due to some other reason, not due to the interaction, between this ring and that atom, not because of that. Maybe because of another hydrogen bonding between because hydrogen bonding is the strongest one among these van der Waals forces. Therefore, if there is a strong bond between that and another atom here, then this will be like this only. So because of that position, this becomes somewhat closer, then we should not take a decision that it has interaction between this atom and the ring. So that we must be very careful, and wisely we have to decide which one is really true. So that is our duty, and we should not believe on whatever it is in the listed in the list file is true. So now we can go here and check one by one. C05H5 CG1 we can test. CG5, now we can neglect this one. CG1 is the ring and with the coordination ring. That is not the real pi interactions. That is because of the coordination. The metal is there and other coordinate because of that ring, and whatever the ring is there, it will calculate and give us. And therefore we don't consider it as it has p orbitals and all like our benzene ring. It doesn't have a p orbitals everywhere to overlap with this hydrogen. Therefore, in that cases, whatever that CG1 is involved, we can neglect. So in that cases, we don't consider this, and we take only this. In this cases, because CG1 is the coordination atom with the metal, central metal atom. And here C4S and H4SB, then we have to find out this. And with the CG3 we already know, and we have to find out the C4S and H4SB. So we can go back to this and find out whether the symmetry is same. If the symmetry is same, then it will be with the same molecule that we have obtained now. Otherwise, we have to obtain another symmetry, another molecule which has a different symmetry from this. So this one is CG. Yeah, this one is CG3. Yeah, this is CG3. This is CG4. And this is the original one that we obtained. Other symmetric one, other symmetric molecule is here. Now, let us check whether it is the same symmetry. Now, 4464. This symmetry is 4464 from this. So it is different symmetry. Therefore, it doesn't have interaction with this. And also it is from the C4S H4SB, that is from the solvent molecule. C4S, yeah, from the solvent molecule. So we have to find out the solvent molecule here. So from this we can find out C4S. This is C4S here. This is C4S and C4SB. So this is C4SB. So this hydrogen atom is involved. So we located that hydrogen bond. Now we have to bring the others molecule which is having the CH pi interaction with the CG3 ring of the another symmetric molecule, not with this molecule. So that has a different symmetry. Therefore, we have to find out that also. So now we have located the hydrogen. Now we have our now intention is to find out this find out the other symmetric molecule. So that as we have done before, then we can go to connectivity, and here we have drawn one the cylinder, the polyhedron. Therefore, that dummy atom also will be included here. So we have to remove those things again. So we can check again from here and see whether the dummy atom is involved. Here, dummy atom is in the question mark. So we can uncheck these things. We can remove this. And all whatever this question mark involved, we should remove. Otherwise, it will bring the dummy atom and the related pi ring. So it will be very big. So when you bring obtain new molecule, this will disturb you. So you should remove anyhow. So these are the question mark, whatever where the question mark involved with another atom, and we can uncheck those things. That is very essential. Otherwise, it will disturb you always. Okay, shall we here also, and make sure that you have removed everything. MO this also we can remove. Okay, so MOH also we are that we are okay. Then after that, now it is very clear. Now again we can go to build and connectivity, because we are going to connect with this with the other carbon atoms, p orbitals of the other carbon atoms in the CG3 ring of another molecule. So then we have to guess that with what atoms we can connect this hydrogen. So only CH, there will be carbon atoms only. So with this hydrogen, we can connect the carbon atoms of the CG3 ring, and by increasing the maximum distance of the bond. So we can go to connectivity again. So find out the CH distance, CH here. No? CH, the default maximum will be 1.296. Now we can increase to, because now our distance will be around how much? HCG distance 2.79, so around 2.8. So we can make it to 2.8, or we can, if we increase to 2, what will happen? This you will not get it because it is 2.8. So we can make it to 3 maximum. 3, then it will be there. Some other atoms also will come that we can delete it later. So we can make it with this. Then select this hydrogen H of 4SB and right click and what is a complete, sorry, not complete, fill coordination sphere. If you don't click this one, then it will not give you anything, because that fragment is already completed, so it will not give you anything. So only fill coordination sphere. So within that range, it will search and find out what are the carbon atoms which is nearest within that sphere. So we can now it found within the sphere here. So it additionally connect these things that we know already. So we can delete these additional things that already that is connected by this. And see, focus, bring closer and rotate, and see what is again unwanted coordination is here. And these bonds also we can remove, and we can check whether these are CG3. This must be CG3 ring, no? Therefore, we can check it again whether it is CG3. Oh yeah, C7, C3. Yeah, these are from the same. Yeah, C5. These are okay. C7, I don't know. If we have suspicion, we can delete it. No problem. Only one atom is enough to get the whole molecule. So now, don't forget to go back and bring it to default value, that is 1. Otherwise, it will bring all the molecules there. So now we can get the molecule here from this fragment. We can complete the fragment, and the new molecule will come here. This is a new one. So we can enlarge and enlarge and see whether it has a really CH5 interaction. Yeah, that pi ring is there, and the hydrogen is pointing towards the ring. So it must be, if this is ring, the hydrogen must be pointing towards the ring. If it is perpendicular, it will be very highest interaction when the angle is coming okay. And if it is 90 and less than 90, then we will not consider it. If it is this or the angle, it will be okay. So if it is this like this, so we will consider it as it may have a pi interaction. That distance is already listed. Therefore, we can connect it now. This is CG 3s. No. No, other one, this one, CG4sB. Yeah, this one. So we can select this hydrogen atom and the interaction between this hydrogen atom and the rings here. All the ring. We can select all the ring. Hydrogen atom plus all the ring, like, and go to polyhedra, build and polyhedra, and construct polyhedra. Here we can go to design and select any color. Must be different color, otherwise it will be confusing. And the transparency, usually I give 0.5. You can give any. You can vary this transparency, that depends on you, but don't make it 1, then you cannot see anything. Okay, then it'll be okay. Now it has drawn. Here, as usual, we will get the dummy atoms here. Here you can, when you bring the mouse here over the atom, then it will show you the dummy atom 1. Then we can click on that and right click and then edit, go to edit and atom design and make it invisible. Make it invisible. Then it will be invisible. Okay. This atom is because we have given that half transparency, 50% transparency. Therefore, you can see the other atoms behind. Not the dummy atom. This is not the dummy atom. So this is the atom here. So you cannot see any dummy atom here. So this is how we can draw the solid representation to show the pi interaction and CH pi interaction. So this is to draw CH pi interaction. So likewise, if you have even the metal pi interactions with the metal and the oxygens or the oxygen and the pi ring interaction. So whatever it is in the table, then you can find out and decide whether it is significant. And after that, you can draw like in the similar way. There is no special way. Only this polyhedron is the way to use this kind of interactions and connect molecules like this in different symmetric molecules will be connected together by means of these all different interactions. Again, now we have completed the CH pi interactions, and now we can move on to scroll down and see whether we have any other type of interactions, any shorter interactions possible. Here, no such interaction, but hydrogen bonding will be there down. So we will go to the hydrogen bonding table. So after pi interaction and CH pi interaction, then big table will come, big tables. Then after that, we can find out this hydrogen bond interaction. Now it will come. As of non-hydrogen intermolecular contacts. Intermolecular, yeah. Here. Yeah, analysis of potential hydrogen bond interactions. This is the table. So you can find out easily. If you are familiar with this list file, then we will find only these tables are important, and location also we can easily find. Okay, now we can see this is donor atom, and this is the hydrogen, and this is acceptor. So donor, acceptor. So we will find out which is donor and which is acceptor, and the symmetry code of that, and the HA distance, DHA angle. Angle also we have to check, because if the angle is short, then it will not have a considerable interaction, because hydrogen bond, if it is 180, it will be perfect. So ideal. So we will not get always the exactly 180 angle. So it will be 170, sometimes 60 or 50 or even 40, 30, 20, 110. Then we have to be careful. So if it is less than 110 or around 100, then we usually neglect those things, because that overlapping, extent of overlapping will not be that much high. Therefore, it will be very weak. So we have to check again whether it is possible or not. And if it is essential and no way, there must be some interaction, this is maybe this one, then only we can consider. Otherwise, we simply neglect those things. If the DHA angle is less than 110, we can neglect. Okay, these are the, through experience, we have taken this decision, and we have some boundaries. So from our experience, we learn. So that you also can use this. And again, intramolecular, you see the distance is 105. So we can intramolecular, you can again visit and see that whether it is feasible. That will not be, because it will be much folded, means very less angle, then there will be no such intramolecular interaction. So we can neglect this intramolecular first, and then wait a little bit. I just connect the speaker. Whether you have spoken anything, I don't know. Have you asked any questions so far? Anything I missed? Because my speaker was off. So I didn't ask any, I didn't hear any voice from you. So have you asked any questions?
No, sir. No, sir.
Okay, okay, I can. Okay then. Okay, then now we can see the hydrogen bond interactions. Then we can say that this is not feasible. So we can neglect, others are feasible. 177 is very high, and this is also very good, and this is also very good. Therefore, we can consider, and still we have to check. O5, H5, O1S, isn't it? So O5, H5, O1S. Okay. DH is this, HA distance is this, DA distance also we can consider. DA distance must be, whether that's okay. And this is somewhat high. These are somewhat higher. It goes around 3. But okay, let us see. So O5, H5, O1S. O5 is a donor. This is H5 is a hydrogen bond, and O1S acceptor. Okay, we will check it.
Sir.
Yeah.
So selecting that hydrogen bonding only by that angle, or by that distance also we can use, no?
Distance also, yeah. Yeah.
So
DA
what is that distance should be minimum or max?
We cannot say much, but if it is around 4, about 3 is also we have taken. Depends, but if it is around 4, then we can surely neglect. Is 3.1 or 2, then we have taken also. Even 3 also we have considered. That depends on the cases. If there are a few interactions, then we have to consider this. There are many other interactions, then we can consider it as weak forces. Here we can consider this. Angle is very important. First we have to check the angle, then later we can check others, and after that we can see this and decide with the DA distance. And the HA distance also we can check. HA distance is very short here for this. So this has actually very high interaction. The angle is also very high, and the HA distance and the DA distance is also very low. But this is intramolecular, so we have neglected. So when we compare this and this, these are very much weaker than this when we compare this. So we can take only this and say these are weaker interactions. Or even we can draw and show it. It is not a big problem, but still we have to say by a statement that this is stronger than these two. Then it is okay. Otherwise, we can neglect this and say that these are weaker hydrogen bond forces. So therefore, we have considered only the significant or the strongest hydrogen bond interactions found in the crystal structures. And now we can see how to draw this one. The O5, H5 and O1S. We can go back with this symmetry H55. That symmetry is again XYZ. Here it is not given. So maybe with the same that we will see, and O1S maybe acceptor O1S from solvent. Yeah, from the solvent. That is why the symmetry is different. So we can check whether it is possible. Yeah, it is possible. No, now you can see here. This is the this is O1S here. This is O5, and this is H5. This is possible. Distance is also very short, so this is possible. So we can draw these two. So the molecule has a hydrogen bond interaction between the solvent and the molecule. So the solvent has this hydrogen bond interaction with this. So that is why it is showing it as a intermolecular hydrogen bond. But actually, this is also, if we consider it as a whole thing is as a asymmetric molecule, then it is also coming under intra. But no, we cannot say it is intra, but actually intermolecular. But it is in the same symmetric, same asymmetric molecule. So we can again select these or locate these two and go to build and insert bonds, build and insert bonds, then select these two. Then we can make a bond. Yeah, now we made here, we made the bond. Now we can change into a different color because we have to show it as a hydrogen bond, not like normal bond. So we can go to edit and bond design and change this color to green. We usually use green. And fragment also we can put around 5 fragments, dotted lines. And thickness, if you want, you can increase the radius, or even thick is here, okay, or visible thick is okay. And if you want to increase the radius, you can increase, that is not a problem. It will become higher, bigger. That depends on that, as you wish, you can make it. So this shows that it is a hydrogen bond interaction between this hydrogen and this oxygen atom, O1s, the solvent, oxygen. So likewise, we can find out even the other thing and draw even the weakest thing. Also, you can draw C9H9 O1s, again with the O1s. So the solvent again forms another interaction with the C9H9, but different symmetry, not with the same symmetry here. This is a different. So we have to obtain another symmetric by as I showed you how to get the another one, that you can change the connectivity and get the other molecule and connect this. And likewise, we can obtain for this also C12H12O3, C12H12O3 with the different symmetry. C12H12 is from the C4 ring. So we can just see C4. Yeah, this is C4, C12, 11. Yeah, this one is C12. Yeah, C12, H12. Yeah, this is C12, H12. And the interaction is between C12, H12 and O3. O3. O3, this is O2, this is O4, this is O3. But this will not have interaction with this. Therefore, we have to find out somewhere it must be another molecule that must be somewhere here around this. So we need to find out. We need to find out. So we can obtain the molecule by drawing here, by changing the connectivity as we have done before. Before we do the changes in the connectivity, we have to check again. We have obtained another duplicate atom or the dummy atom. That also must be unchecked again. So we can check again whether we have unchecked all these. Yeah, all are okay. Yeah, it's already unchecked. Therefore, now we can change the connectivity. Now, what is the connectivity now that we have to make is CH interaction is with the oxygen atom. So OH distance must be increased. So we can go to connectivity and increase the OH distance. OH. Oh. Yeah. This to what extent we need to increase, that we can check again here. This must be HA. HA distance will be around 2.49. HA distance be 2.49. So we can increase to 2.2 is not enough. Therefore, we can increase to 3 and see whether and yeah, what are the other atoms also will additionally will come. Let us see fill coordination and see which is we can do undo by Control Z. Undo will come. Yeah, undo will come. Then we can select only that. If you don't select this atom, and it will connect all. So we have to carefully select only that atom, and on that selected rectangle or square, you have to right click and fill coordination. Only that will come. Others will not come. Otherwise, all will come. So you can take it here and see this. We don't, yeah, we can have this, and we can now change it to different color, because after bringing all molecule, it is very difficult to find out exactly which molecule we have obtained and what is the atom that we have connected. So that is for that purpose, we can make it to different color so that we can easily find it. Or blue, or which one you like? This one, or whatever it is. Okay, so it will be different. So we can, after obtaining this one, we can easily locate it. So now don't forget that we have to again bring it to default value and okay. Then after that we can select that atom, and complete fragment. You have to get the complete fragment. So now that complete fragment came, we have to find out it. So by rotating here, that is why I have and separated this is the one. So we obtained this is the new one. Okay, so now we have a CH this interaction that is connecting here, no, through this. So we can consider this also, no problem. So we can consider this also and connecting this and bring it to different color as we have made earlier. We can make it to green, which green you want, whatever it is, and 5 fragments and made to, how much we have put earlier? I don't know, I forgot. So I may just make it like this. So now it is okay. Now we have interaction, the CH5 interaction between this CH hydrogen bond interaction between this and this is classical and non-classical hydrogen bond interactions are possible. Here, if the donor atom is carbon, then we say it's a non-classical, and if that has electronegative atoms, nitrogen, oxygen, or sulfur, like, then we call it as classical hydrogen bond interactions. So in this case, this is non-classical hydrogen bond interactions. So the first case is classical, O and O. Donor is electronegative group, electronegative atom. Therefore, classical hydrogen bond interaction. These are non-classical hydrogen bond interactions. All these. So these are this will be very much weaker than this usually. So we can show that in addition to the classical hydrogen bond interaction, we have non-classical hydrogen bond interaction as well. So that can be mentioned. And this also we can find out. This also similarly you can find out this also C9, H9, because this can be considered. Because these are non-classical hydrogen bond. This will be somewhat weaker than this one. So it is obvious. So we can say in addition to the classical hydrogen bond interaction, we have non-classical hydrogen bond interaction additionally supporting the this assembly of this crystal. So these are the ways to find out and draw these hydrogen bond interactions and all these other interactions. Then we can clearly rotate this after drawing everything. Then we have to find a suitable position where you can easily see all interactions and label it. So this all hydrogen bond interactions, pi-pi interactions, CH-pi interactions, so all must be visible very clearly. So in that we have to rotate and see the exact position where you can clearly see all these interactions that you have drawn, and then label it. So in this case, if you want to label that, you can click the atom. This is a donor, and the acceptor must be labeled. So the right click on that and add atom label. So in this atom label, you can make it a dark or black, and here also you have to, again, as I showed earlier, atom labels, atom symbol, and you can make it to 5, somewhat bigger size, otherwise it will be very small, and you can increase more also, that is not a problem. Then it will come. So you can click it and keep it, drag it and drop it here. So it will be visible. So in this case that C3s, no, this is not the atom, exact atom. So we have to rotate and see other atom. Yeah. So we have to find a suitable. Yeah. So now it is okay. Now we can locate it and add atom label and dark black color atom symbol, and you can increase here, and after that you can just put it here. So you can see the forest. And any other labels if you want to put, then you can label here the hydrogen bond. Hydrogen bond, you can just donor and acceptor, both can be labeled. So the labeling, you can go to add and atom labels. There also you can just do this atom symbol and 5 size also you can select, change, and then okay. So all will come. Then you can just click it and drop it somewhere very near to that, so that you can clearly see the label. And here also click here and click here and go to add and atom, sorry, go to add where here, yeah, add go to atom label, and here atom symbol. No, not here, 5 here, the size, font size, and here all you can bring it here. So the symbol will be clear, atom symbol. And to represent this, if it is CG3, this is CG3. If you want to put as a CG3 here, then you can go to paint. After saving this, you can go to paint, and there you can put the text, use the text and write on this, very near to this, CG3. Here CG3, CG4, and those things can be, here we cannot label that. Okay, then after that we can bring it to normal and go to, then we have to take the picture, the high quality picture. Then we can move on to tools and the POV ray. then render into bitmap. Here you can set the this resolution as you wish. If you want a higher resolution, you can set it as you wish, and then go to file and select the file in the zip file, then figure 2, then figure 2, whether it is a BMP, yeah, only BMP and PNG is available. So whatever it is, you can save it, and then after that you have to click render. Then rendering will come. So you can see how, when it renders. So now very clear, high quality picture is obtained. So now anyhow we have missed something here, very high quality picture, but the thing is we have missed some part of the atoms here. So again we have to set it close, and we have to narrow down, shrink the molecule so that it will come out. So go to tools again, POV ray, render, then set to the same file, show the same file because we don't want that again, and render. So now also some hydrogen atoms are hidden. So after this game, then we can close it and go down, go back, and now shrink more. Yeah. Okay, then now we can go to tools and POV render, and then the same file, then click render. Can you see the file when it renders the picture file?
Yes.
Okay, sir.
Yes.
Okay.
Yes, it is seen.
Yeah, okay, sir. Thank you. So now a very high quality picture is obtained here. So we can even increase the resolution, depends on our needs. So this is how that we can obtain all these pictures. And if we want to get the packing diagram, then we can go back, or even we can get it from here, packing diagram. Not from here, yeah, yes. Now it'll come like this. So with the existing thing that we can fill. Otherwise, if you want a new one, then we can delete all these things and get new molecule and get the fill unit cell, and it will come without this, all what we have drawn. So we can, yeah, draw it. So now there are some missing, what the buttons are missing. So usually it comes like this. Then what we have to do is we can select it. We can select all the atoms because some of the bonds are missing, only atoms are there. So then right click on any selected atom and go to complete fragments. So say for some fractions are missing. So it will come nicely. Now it came. So yeah, now it is okay. So now we can rotate. Yes, some here we can see some black dots are coming. That is because of the polyhedron that we have done dummy atoms. That dummy atoms must be deleted. Here we have some dummy atoms. When we draw with this, after drawing this, it will come. So we can enlarge it and see, find out the dummy atoms where, yeah, here. We can select by clicking the control key. and delete it. Then we can rotate and all directions and find out the suitable axis. Which one is nicely showing the growing of the layers or crystals, and in that position you can show, and yeah, you have to carefully rotate and see in all directions and which one is showing exactly the layers. Yeah, here also here we can see the axis through which here clearly shows that is through along B direction. And this axis are here A and C. A and C. Here we can put A here, C, and B is here. So we can, after that we can draw it. Even here itself we can put the arrow, but that will not be visible. Usually we get it without arrows and draw it in using picture, using other software like Paint to draw the arrows only. So whatever possible you can. So I just take in one point. We have to set in an exact position so that you also have to show the axis. Otherwise, showing axis is very difficult. Sometimes it will be surrounded by all the atoms. Therefore, drawing here the arrows are very difficult, and putting the labeling or origin and A, B, C are also very difficult. So carefully we have to rotate and see which one is more suitable. Sometimes when we rotate, we lose the exact layers. That also sometimes happens, that in your that is your task. Okay, then now now we can take the picture again, render, and then files. Okay, render 2000 and 1200. Okay, and files and figure 3. It's a BMP. Then render. This will take some time because this contains more molecules, more atoms. Therefore, it will take some time to render. Now this is okay. So we can save it. Already saved. This will be saved in the same folder. Now we can label it. The origin that we have to label, putting arrows here. Here also we can put arrow, and then O, A, C, and B must come here. A, B, C, and then this will be B. So we have to put arrow here, and putting label is somewhat difficult here. So within that, somewhere within this gap, we can put O. Outside is not suitable because the atoms are very crowded. Yeah, within that space we can label. Here also we can label somewhere here or here. So we ourselves have to find the space to put the label. Okay. So that's all. If you want anything, then I can show anything, sir.